In the quiet darkness beyond Neptune, an object designated 3I/Atlas is moving towards the Sun. It is the third interstellar visitor ever detected in human history, but its size is so enormous that according to our best scientific models, it simply should not exist. The data suggests its nucleus, the solid object at its core, is a cosmic monster, a body so massive that finding it now is a statistical impossibility. The object's properties are so profoundly strange that some of the world's most respected astrophysicists are openly questioning if it is a natural object at all, suggesting instead that it might be a piece of engineered technology. The story of this cosmic anomaly began on the night of January 7, 2023. High atop the volcanic peaks of Hawaii, a network of telescopes was performing its nightly duty. This is the Asteroid Terrestrial Impact Last Alert System, or ATLAS for short. It is not designed to gaze at distant galaxies or nebulae. Its purpose is far more immediate and practical. It is a planetary defense system, an unblinking sentinel tasked with scanning the entire observable sky every 24 hours, searching for any moving object that might pose a threat to Earth. The ATLAS system consists of 4 telescopes, 2 in Hawaii, 1 in Chile, and 1 in South Africa. This global distribution allows it to maintain continuous observation of the night sky, passing the watch from one hemisphere to the other as the Earth rotates. Each telescope is a relatively small half-meter instrument, but what they lack in size, they make up for in speed and breadth of view. They can image a patch of sky 100 times larger than the full moon in a single exposure, capturing millions of stars at once. Software then meticulously compares these new images to previous ones taken of the same region. Anything that has moved or changed in brightness is automatically flagged for further investigation. 99.9% of the time, these flagged objects are known asteroids on predictable orbits, their paths well understood and cataloged. They are the familiar residents of our solar system. But on that January night, the system flagged a faint, slow-moving point of light that was not in any catalog. It was a complete unknown. Following standard procedure, the object was given a provisional designation, C/2023A3. The C indicated that astronomers initially believed it was a comet. The 2023 marked the year of its discovery. The A3 signified it was the third such object found in the first half of January. This bureaucratic-sounding name concealed a truth that would soon send shockwaves through the astronomical community. It was a name that would not last for long. As news of the discovery spread, observatories around the world focused their more powerful instruments on the faint newcomer. Every astronomer wanted to plot its trajectory, to understand where it came from and where it was going. The process is a digital form of triangulation. By taking multiple observations over several days and weeks, astronomers can trace an object's path through space with incredible precision, calculating its speed, direction, and the shape of its orbit around the Sun. Most objects within our solar system, from tiny asteroids to massive planets, travel in closed loops called ellipses. An ellipse is an oval shape, and an object on such a path is gravitationally bound to the Sun. It is a permanent member of our solar system, destined to loop around our star for billions of years. Comets from the distant Oort cloud, for example, have extremely long and stretched out ellipses, but they are ellipses nonetheless. They always come back. The data that came back for C/2023 A3 showed something entirely different. Its path was not a closed loop. It was a hyperbola. A hyperbolic trajectory is an open-ended path. An object on such a course is moving too fast to be captured by the Sun's gravity. It will swing past our star once and only once before continuing its journey into the void, never to return. This was the unmistakable signature of an object that was not from around here. It was a true interstellar traveler. With its origin confirmed, the object was officially renamed. It became 3I/ALS. The 3 because it was the third confirmed interstellar object, and the I for interstellar. But while this confirmed its exotic origin, it did little to explain its nature. As more data was collected, a startling picture began to emerge. The first 2 interstellar visitors had been scientific sensations, but 3I/ALS was on its way to becoming a legend, a puzzle that challenged our fundamental assumptions about the universe. The first hint that something was deeply unusual about 3I/Atlas came from its activity. Like a typical comet, as it drew closer to the Sun, its surface began to warm. Ices that had been frozen solid for millions or billions of years started to sublimate, turning directly from a solid into a gas. This process created a vast glowing cloud of gas and dust around the object's solid core. This cloud is known as a coma, and it can swell to be hundreds of thousands of miles across, dwarfing the nucleus hidden within. This coma brilliantly reflects sunlight, which is why we can see comets from Earth. It also makes determining the true size of the nucleus incredibly difficult. Looking at a comet is like trying to gauge the size of a flashlight bulb while it is switched on inside a thick bank of fog. All you see is the diffuse glow, not the solid object creating it. To figure out the size of the nucleus, astronomers had to rely on a far more subtle and clever method of measurement. A team of researchers led by a prominent and often controversial Harvard astrophysicist began to analyze the object's trajectory with unprecedented precision. They were not just looking at its path, but for tiny deviations from that path. They were searching for something called non-gravitational acceleration. This phenomenon is a key diagnostic tool for understanding comets. It is a direct consequence of the outgassing that creates the coma. As a comet's surface heats unevenly, it does not release gas smoothly in all directions. Instead, jets of gas and dust erupt from active regions on the nucleus, like miniature rocket engines. These jets, while individually weak, exert a constant, gentle push on the comet's core. This tiny but persistent force is enough to nudge the comet slightly off the path that gravity alone would dictate. The effect is minuscule, but with modern telescopes, it is measurable. The amount of this non-gravitational push tells you something crucial about the nucleus itself. The physics is straightforward. Imagine two objects in space, both with rocket engines of the same power strapped to them. If one object is small and has very little mass, the engine will push it around easily, causing it to accelerate significantly. If the other object is gigantic and has immense mass, the very same engine will barely be able to budge it. Its acceleration will be very small. In the case of a comet, the strength of the engine is determined by the amount of outgassing, which can be estimated by the brightness and size of its coma. The mass is the unknown variable astronomers want to solve for. 3I/ATALAS presented a baffling contradiction. Its coma was vast and vibrant, indicating a tremendous amount of outgassing was taking place. Its jets were firing powerfully. This meant it should have been experiencing a significant non-gravitational push. But when the team analyzed its trajectory, they found that it was barely being pushed at all. The non-gravitational acceleration was shockingly almost immeasurably low. The object was holding its course with incredible stability, resisting the powerful forces of its own jets. There is only one way to reconcile these two facts. The nucleus at the heart of the coma had to be colossal. It had to be so incredibly massive that even the constant thrust from its violent outgassing could hardly alter its path. The numbers the team calculated were difficult to comprehend. Their analysis pointed to a solid body with a diameter of roughly 3 miles or about 5 kilometers. The estimated mass was over 33 billion tons. This figure is staggering. For context, the nucleus of a typical comet from our own solar system is usually less than a mile across. The previous interstellar comet, 2I/Borisov, was estimated to have a nucleus less than half a mile in diameter. This new object was not just larger, it was in a completely different category. The 33 billion ton mass estimate means 3I/Atlas is potentially 3 to 5 orders of magnitude more massive than the other interstellar objects we have seen. This does not mean 3 to 5 times heavier. An order of magnitude is a factor of 10. This means 3I/Atlas could be anywhere from 1,000 to 100,000 times more massive than anything we have seen from beyond our solar system. This discovery immediately created a profound statistical problem in nature, and across the cosmos, there is a general rule: small things are common, and large things are rare. There are countless small pebbles for every large boulder. There are billions of small stars for every giant superstar. The same principle should apply to the population of objects wandering the space between stars. There should be a vast number of small interstellar objects for every truly massive one. Based on our current models of how planetary systems form and eject material, we should have detected dozens, if not hundreds, of smaller interstellar visitors before ever stumbling upon a giant of this scale. Finding 3I/Atlas as only the third object is like reaching into a bag of marbles you assume contains millions of tiny glass beads and a single bowling ball, and pulling out the bowling ball on your third try. The odds are astronomically against it. When observational data defies statistical models so dramatically, it is a powerful sign that the underlying assumptions of those models are wrong. The existence of 3I/Atlas suggests one of two things. Either we have just witnessed a 1 in a trillion statistical fluke, an event of pure dumb luck, or the space between the stars is populated in a way we had never imagined. It suggests that cosmic monsters like 3I/Atlas are far more common than our theories predict, and we have been blind to them. The mystery deepened further when preliminary, and still unconfirmed, reports about its composition began to circulate. Some initial spectroscopic analyses hinted at the presence of nickel in the coma's gas. While detecting elements is standard practice, this finding was notable for what was absent. There were no corresponding traces of iron. In the natural universe, this is a massive red flag. Nickel and iron are cosmic siblings, forged together in the violent hearts of dying stars. Through the process of stellar nucleosynthesis, stars fuse lighter elements into heavier ones. Iron and nickel are created near the end of a massive star's life. Because of their nuclear properties, they are almost always produced in concert. When that star explodes as a supernova, it scatters these elements throughout the galaxy. They mix with gas and dust clouds that eventually form new stars, planets, and asteroids. As a result, wherever you find natural deposits of nickel in the cosmos, you almost invariably find iron right alongside it. To find one without the other is exceptionally strange. It hints that some non-natural process has separated them. On Earth, the primary process that separates nickel from iron on an industrial scale is refining. It is an artificial process used to create pure metals for advanced manufacturing and technology. This single tantalizing clue, combined with the object's impossible size and the statistical anomaly of its discovery, began to fuel more radical speculation among astronomers. The quiet detection from a mountaintop in Hawaii had transformed into one of the greatest astronomical puzzles of the modern era. An object that should not exist was now hurtling deeper into our solar system, and humanity was finally in a position to watch it arrive. This was not the first time a visitor from the stars had confounded scientists, but this time the circumstances were different. This time we would be ready. To truly grasp why 3I/Atlas is causing such a scientific upheaval, we must look at the two visitors that preceded it. Before the year 2017, the concept of observing an object from another star system was purely theoretical. Scientists assumed such objects existed, cast adrift from their home systems, but the sheer vastness of interstellar space made the odds of one passing close enough for us to detect seem infinitesimally small. Then, on October 19, 2017, that changed forever. The Pan-STARRS telescope in Hawaii, a survey instrument similar to Atlas, spotted something new. The object was initially designated a comet, then an asteroid, but as its trajectory was calculated, astronomers realized it was on a hyperbolic path. It was our first confirmed contact with a piece of another solar system. It was named 1I/Oumuamua, a Hawaiian word meaning scout. The name proved to be remarkably fitting. Oumuamua was nothing like astronomers had expected. It was not a fluffy, roundish comet. Observations of its light curve, the way its brightness flickered as it tumbled through space, suggested it had a bizarre, extreme shape. It was thought to be very elongated, perhaps 10 times as long as it was wide, like a cosmic cigar or a flat, thin pancake. It was small, estimated to be only a few hundred yards long. The strangest thing about Oumuamua, however, was its motion. Like 3I/Atlas, it exhibited non-gravitational acceleration. It was accelerating away from the sun faster than gravity alone could explain. But unlike a comet, Oumuamua showed no visible signs of outgassing. There was no coma, no tail of gas and dust. It was accelerating as if something was pushing it, but there was no evidence of any propulsion. It was a silent, dark object, moving in a way that defied explanation. This mystery sparked a firestorm of debate and a host of competing theories. Some scientists proposed it could be a hydrogen iceberg. The idea was that an object made of solid hydrogen would sublimate and produce a gas tail, but because hydrogen gas is transparent, the tail would be invisible to our telescopes. The problem with this theory is that no one knows if a hydrogen iceberg could even form, let alone survive a journey of millions of years through interstellar space. Another theory suggested it was a nitrogen iceberg. a fragment chipped off a Pluto-like planet orbiting another star. A chunk of frozen nitrogen would also produce a mostly invisible gas as it warmed, potentially explaining the thrust without a visible coma. This idea was more plausible than the hydrogen iceberg, as we know nitrogen ice exists in our own solar system. However, it would require a very specific set of circumstances to create and eject such an object. It was then that Avi Loeb, the same Harvard astronomer now studying 3I/ATLAs, put forward his most famous and controversial hypothesis. He argued that Umanyam's strange comless acceleration could be perfectly explained if it were not a natural rock. He proposed it was an artifact of an extraterrestrial civilization. Specifically, he suggested its motion was caused by the pressure of sunlight, solar radiation pressure, pushing on a very thin, lightweight object. It was, he argued, a solar sail. A solar sail is a theoretical form of spacecraft propulsion that uses the momentum of photons from a star to generate thrust, much like a sailboat uses wind. To be effective, a solar sail would need to be incredibly large but also incredibly thin and light. This would give it a shape not unlike a pancake, matching one of the interpretations of Oumuamwa's light curve. The scientific community was deeply divided by this proposal. For many, it was an unsupported leap to an extraordinary conclusion. For others, it was the only explanation that fit all the bizarre data. The debate over Oumuamua was fascinating, but ultimately frustrating. It was moving incredibly fast, and we had spotted it on its way out of the solar system. By the time we understood how strange it was already receding into the darkness, too far and too faint to study with even our most powerful telescopes. It left us with a cascade of questions and almost no answers. It was a fleeting glimpse of something truly alien, whether natural or not. Then, just 2 years later, in August of 2019, it happened again. This time, the discovery was made by an amateur astronomer named Gennady Borisov. The second interstellar visitor, named 2I/Borisov in his honor, was immediately different. Unlike the mysterious Oumuamua, Borisov looked and behaved exactly like a comet. It had a clearly visible coma and a long sweeping tail of dust and gas. For many astronomers, the discovery of Borisov was a huge relief. It seemed to confirm the standard model. It suggested that Oumuamua was the strange outlier, the one-in-a-million weirdo, while Borisov was the norm. It proved that ordinary, familiar-looking comets did indeed travel between the stars, just as our theories had predicted. The cosmos was perhaps not as strange as Oumuamua had made it seem. But even Borisov held its own secrets. As astronomers studied the light from its coma, they were able to analyze its chemical composition. They found it had an unusually high concentration of carbon monoxide, far more than any comet ever observed from our own Oort cloud. Carbon monoxide ice only stays solid at extremely low temperatures, much colder than the regions of our own solar system where comets are thought to form. This chemical signature was a clue to its birthplace. It suggested that 2I/Borisov had formed in a very different, much colder environment than our own comets. The most likely candidate was the protoplanetary disk around a red dwarf star. Red dwarfs are much smaller and cooler than our Sun, so a comet forming there would naturally incorporate more exotic ices like carbon monoxide. Borisov was a fascinating piece of another solar system, but it was small, with a nucleus estimated to be less than a mile across. It fit our models more or less. And that is precisely why 3I/Atlas changes the entire game. First, we found a bizarre tiny non-comet that accelerated in a way we could not explain. Then, we found a small, relatively normal-looking comet with a weird chemical signature. Based on this emerging pattern, and on our statistical models, the logical expectation was that the next interstellar visitor would be something similarly small. Instead, we found a behemoth. 3I/Atlas is not just a little bigger. It is a fundamentally different class of object. It seems to combine the strangest aspects of both previous visitors. Like Borisov, it is an active comet with a large visible coma. But like Oumuamua, it has a mysterious acceleration issue. Not because it is moving too fast, but because its movement is too steady, too resistant to the forces acting upon it. Its immense mass is the central mind-bending fact that throws all previous assumptions into chaos. Finding Oumuamua first was strange enough. Finding Borisov second seemed to bring us back to a sense of normalcy. But finding 3I/Atlas third, a cosmic leviathan, suggests that our entire understanding of the interstellar object population is fundamentally flawed. It is like an ecologist sampling a pond. The first fish they pull out is a piranha. The second is a goldfish. The third is a blue whale. At that point, you have to conclude that this is no ordinary pond, and your sampling methods or theories are completely wrong. This pattern of cosmic oddities forces us to consider that these are not just random rocks. They might be messengers, carrying profound clues about how solar systems are truly built across the galaxy. Or, as some are now willing to consider, they might be something else entirely. With an object as profoundly strange as 3I/Atlas, mainstream explanations begin to fray at the edges, leaving room for more imaginative and frankly more exciting possibilities. Two bold theories have emerged, each attempting to answer the fundamental question, what is this colossal object, and why is it here? The first theory transforms 3I/Atlas from a random wanderer into a key player in the story of cosmic creation. It is a natural explanation, but one with revolutionary implications. The second theory takes a darker, more technological turn, suggesting the object is not a player in the game of creation, but a piece from a different game altogether. The first idea comes from the work of astrophysicist Suzanne Faulkner and her colleagues. It is a simple but beautiful concept that seeks to solve one of the biggest problems in planetary science. Faulkner suggests that 3I/ATLS could be a planet-making seed. For decades, there has been a major inconsistency in our understanding of how giant planets like Jupiter and Saturn form. The leading theory is called core accretion. The core accretion model begins in a young solar system, with a newborn star surrounded by a vast rotating disk of gas and dust known as a protoplanetary disk. According to the theory, tiny dust grains in this disk randomly stick together, forming larger clumps. These clumps grow into pebbles, the pebbles into boulders, and the boulders into larger bodies called planetesimals. Eventually, over millions of years, these planetesimals collide and merge to form a solid core, 10 to 15 times the mass of the Earth. Once this massive core is formed, its gravity is strong enough to rapidly pull in huge amounts of gas from the surrounding disk, creating the thick atmosphere of a gas giant like Jupiter. The problem is the timeline. This process of growing a core from tiny dust grains is incredibly slow. Computer simulations consistently show that it can take tens of millions of years to form a core large enough to trigger gas accretion. But the protoplanetary disks where planets are born do not last that long. The intense radiation and powerful solar winds from the young, energetic star typically blow all the gas and dust away in just a few million years, usually less than 10 million. This creates a critical bottleneck. It is a race against time that our models keep losing. The planetary cores do not have enough time to form before the raw material they need to build a planet is gone. How then did Jupiter and other gas giants get so big so fast? Faulkner's theory offers a stunningly elegant solution. What if the cores do not have to form from scratch within the disk? What if they arrive pre-packaged, fully formed from interstellar space? Imagine a young solar system struggling to build a planet. Into this swirling disk of gas and dust comes a visitor like 3I/Atlas, a solid 3-mile wide body with immense mass. It is a ready-made planetary core. Instead of needing millions of years to grow from dust, this interstellar seed can immediately start using its substantial gravity to pull in gas and material from the disk. It would act as a gravitational catalyst, kick-starting the planet-building process. This could slash the time needed to form a gas giant from tens of millions of years to just a few million, neatly solving one of planetary science's most persistent headaches. The theory makes a testable prediction. If this interstellar seeding is a primary mechanism for building gas giants, then the ability of a young solar system to capture these wandering cores would be a critical factor. Faulkner's simulations show that larger, more massive stars, with their deeper gravity wells and larger protoplanetary disks, are much better at capturing these interstellar objects than smaller stars. Therefore, you would expect to find gas giants more frequently orbiting larger stars. When we look out at the thousands of exoplanets we have discovered, this is precisely what we see. Observations confirm that gas giants are indeed statistically more common around bigger, more massive stars. It is a perfect match between the theory and the observational evidence. From this perspective, 3I/Atlas is not just a comet, it is a potential world builder, a wandering seed of creation. But then there is the other theory, the one championed by Avi Loeb. Loeb looks at the exact same data, the enormous size, the statistical unlikelihood, the strange stability, and sees not a seed, but a machine. He argues that the sheer improbability of finding such a massive object so soon points decisively away from a natural origin. For him, the fact that nature produces exponentially more small objects than large ones is a fundamental principle. We should have seen a fleet of tiny interstellar pebbles before we found one giant boulder. Finding 3I/Atlas now is, in his words, a clear sign that we are missing something fundamental about what is out there. He also points back to the strange, unconfirmed reports of nickel without iron as another provocative clue. What natural process separates these cosmically linked elements so cleanly? Loeb's answer is industry. He entertains the speculative but thrilling idea that 3I/Atlas could be of technological origin. He is not necessarily saying it is a piloted spaceship, crewed by aliens. The possibilities are much broader. It could be an autonomous probe sent by a distant civilization, similar to our own Voyager probes, but on a vastly grander scale. It could be a piece of debris from a massive alien construction project, like a fragment from a partially completed Dyson sphere or some other megastructure. It could even be a defunct piece of machinery, a derelict from a civilization that died out millions of years ago. For Loeb, the collection of anomalies is simply too powerful to ignore. The oddly low acceleration, the colossal size, and the potential chemical oddities are all provocative hints that demand we consider possibilities beyond the natural. This idea resonates with many because it taps into our deepest questions about our solitude in the cosmos. While most mainstream scientists urge caution, emphasizing that a natural origin, however strange, is still the most likely explanation, Loeb argues that we must at least be open to the possibility of the technological. He argues that to dismiss the idea out of hand is an act of hubris, an assumption that we already know all the forms that matter can take. After all, the universe has surprised us time and time again. With Oumuamua, we missed our chance. We saw it too late as it was leaving. We were unable to get a good, detailed look, leaving it as an eternal mystery. This time with 3I/Atlas, we see it coming from a long way off. We finally have the chance to study one of these visitors up close. This time humanity is ready. Unlike with Oumuamua, which was gone before we truly grasped its significance, 3I/Atlas was detected far out in the solar system, while it was still beyond the orbit of Saturn. This gives scientists years to prepare a cosmic welcome. We will not just be watching from the ground. The most shocking fact is that we have robotic eyes and ears already in space, some of which are being repurposed to wait for its arrival. The European Space Agency, or ESA, is leading the charge, preparing two of its key scientific assets currently orbiting Mars. The first is the Mars Express Orbiter, a venerable spacecraft that has been studying the red planet since 2003. The second is the more modern ExoMars Trace Gas Orbiter, launched in 2016. These probes are perfectly positioned. As 3I/Atlas makes its closest approach to the Sun, its trajectory will carry it relatively close to the orbit of Mars. Engineers at ESA are planning to use these orbiters to get a view of the object from a completely different perspective than Earth. They will be able to perform detailed spectroscopic analysis of the coma, which could confirm or deny the presence of anomalous chemicals like nickel without iron. They can attempt to image the nucleus directly, perhaps giving us our first true measurement of its size, and maybe even its shape. This will be our first opportunity to study an interstellar object from a vantage point in space. Back on Earth, every major telescope, from the newly commissioned Vera C. Rubin Observatory in Chile to the Hubble and James Webb Space Telescopes, will be trained on the object as it gets closer and brighter. The goal is to collect as much data as possible across the entire electromagnetic spectrum, from radio waves to gamma rays. Every photon collected will be a piece of the puzzle. The questions are profound. Is 3I/Atlas a remnant from the dawn of another solar system, a planet seed that can teach us how worlds like our own are born? Did a galactic delivery service help build our world billions of years ago? Or are we about to get our first unambiguous look at a piece of alien technology, a discovery that would forever change the course of human history? For the first time, we have the time and the tools to find out. The universe has sent us a message in a bottle, and we are finally ready to read it.